Okay, getting into Module 9, our second last module, and the most exciting module with no bias from Karina. We are getting into microwave remote sensing. This is also a special beast and special kind of technology that we are working with. It is a super cool kind of remote sensing. There's so many different applications that we can do with it, and things that we haven't been able to do before in the past, such as like optical light can't actually see into objects, where microwaves, I can actually go into objects. Another exciting thing with microwaves is, you know how we talked about X-ray vision? We wanted to be able to see through walls. Well, now microwaves, we actually can use microwave glasses, and we do actually see through walls. And there's a lot of really exciting nature that comes with that. If you can think back to the whole idea of like the Star Trek, can't remember the exact name of it, but that Star Trek medical system that they had, and they would lay down on the bed, and then they would use like a wand over top of them to really like detect what's going on with their body. This is a possibility to do that with microwaves. So really, really exciting stuff is coming out of the microwave world, especially in the biomedical industry. And so this is like a little bit of my background, right? I did my master's degree. I was looking at using interferometry. I was looking at how much does the land subside over a season in the Arctic, and it was that was like the first time that it was being used for that kind of a application. And then now the Canadian Centre for Remote Sensing had been using my thesis to look at how land is heaving when with fracking. So that's another application you never would have thought would have sprouted from that. Then I moved up to the Arctic and I started doing stuff as looking at thicknesses of snow on sea ice and how that is going to impact climate models that we are using right now. And then now I'm working in biomedical industry, and I'm looking at how microwaves can be used to detect changes to the breast when they are recovering from breast cancer treatments. Like, these are just absolutely incredible things. They're so cool. This is stuff that you just cannot do with your own eyes. You have to have some sort of special technology to do it, and microwaves is the way to do it. And Canada is actually one of the leading countries in the world for microwave remote sensing in space. So RadarSat 1 and RadarSat 2, those are like the babies of the Canadian Space Agency. And now we have the RadarSat constellation that's getting up. And that one has 5 RadarSat satellites that are working in tandem with each other. And this is just like super exciting. Canada is like such a strong microwave remote sensing country, and it is so important that you guys learn about it in this way. So no enthusiasm from me whatsoever. This is by far the coolest of the objectives. I could spend my entire life talking about this. So using these slides, I'm going to try to keep myself in one spot. So there is that worksheet that I've given you guys, so you make sure you use that as well as you're going through this and going through your textbook for reading. But getting into kind of what is microwave remote sensing. So there's actually 2 kinds of microwave remote sensing platforms. There's an active sensor and there's passive sensors. So an active sensor is one that just that sends and receives signals, right? And we can use that one for imaging and for graphing. And this one is usually known as radar. And so I'm going to use my example with the breast cancer treatment because they actually do a lot of different things, and there's a lot of different ways to do it. So they use radar as well to do that, and that one, like, they create images from it, and they can do like 3-dimensional imaging from that type of system. Now, the problem is that they're very big systems because it needs to have large transmitters and receiver, so it's a big system. And it's really hard to get through a door. It has to have like liquids that are included with it. Like it's just a pretty crazy system. But then we have a passive sensor, which is what I'm working with. And so like some of the passive sensors only receiving, right? The sensor that we have, though, it does send its own energy, but there's a separate receiver on the other side, so it's just receiving that is. So it's kind of a mixture between the active and passive. But our Earth itself, it actually emits its own microwave energy, and we handle that passive energy similar to thermal energy. So a lot of the mathematics and theory kind of relate similarly to thermal. Natural emissions such as snow. Snow has a very high passive microwave remote sensing wavelength, and so during the wintertime, we are being bombarded with a whole bunch of microwaves every time we step outside. Most of the time, we graph only with passive, and that's why the system that I'm working with in the biomedical industry, that it's kind of an active and passive because we can do imaging with it based on the numbers that we calculate from there, and then, but we also get a whole bunch of graphs between like time domain and frequency domain. So each of our sensors has 4 parts. It has a transmitter, a receiver, antenna, and recorder. I'm going to be talking about the active sensors for the most part here. So my transmitters that sends the repetitive pulses. So it sends it out and keeps kind of going almost like a sound wave, right? So it works very similar. And then a receiver receives a reflected signal, and that's so you can get that's what's going to help us create the image. Then we have an antenna, and the antenna is meant for focusing the signal, whether it be sending or receiving, usually for the receiving side. Then we have a recorder, which actually takes that data and puts it like, takes that data and like creates pixels with it. So the antenna can also be used for transmitting, and so depending on which part of the antenna and which component of it you'll be, depending on the sensor, how that antenna is actually set up. So, but it's meant for focusing the signal. So you really want like a hardcore introduction because you really love technology. I've added a system here, so not a system, but a web page, a web link that you can check out the Sentinel SAR instrument, and it has a really good description on there. So if you're wanting to check that out. So the geometry for a microwave image is exactly these little diagrams, and I have one more slide with all this geometry. So we have my satellite that's up top here, and we have the nadir, which you guys should be very familiar with, that goes straight down from the sensor. We have a 90-degree angle from the horizon. That, sorry, not the horizon, but it's called the horizon. It's a 90-degree from the nadir, so it creates a nice little 90-degree angle in the corner there. Then we have the energy that is coming down in a diverging cone, and right down the center of it is known as a slant range. And all the way across from the one point that it sends the data all the way to the last point that it sends the data. If you can imagine this satellite is coming towards you out of the screen. So if it's moving towards you, the slant range is in the center. The point that is closest to the satellite or closest to the nadir is known as the near range. And the one that is the furthest away is known as the far range. And like I said, we have the ground range, which is either 1 pixel or the full swath width all the way across. So it depends on which satellite you're going to be using. So if we were to, again, add some extra angles here. So this is all just the terminology, and on this side we got the angles. So we have our nadir, the horizon, going from the horizon down to the slant range. That's known as the depression angle. The one going from the nadir to the slant range is known as my look angle. And then we've got the incidence angle, which is actually 90 degrees to the ground. So it's not going to be the same direction as the nadir. The incidence angle comes to from the ground. Sorry, I have to apologize. My dog just distracted me. He's chasing after a bug, and he's like knocking over everything in my house at the moment, trying to get a bug. All right. Geometry, continuing on with this. Now, if we were to actually look at the ground, so here's the satellite, and it's like shining down to the ground. We have the near range side, which is the closest to the satellite, and if we can imagine this satellite moving along the screen, down the screen. And then on the far side, we have the far range. So remember, the whole distance between near range and far range is known just as the range. And then just to keep things really confusing, and the length of the pixel, so we have each of our rows of pixels, and so all this whole set of rows that we collect is known as my azimuth. So we have range and azimuth on the ground for the footprint of the satellite, and then we have our range, and then we have the horizon and the nadir and all the other fun stuff in the actual geometry of the flying system. So as a reminder, when you have a row of pixels and the whole swath, like the whole system gets from the near range all the way over to the far range, that is known as your swath width. So I'm going to bring in my talking like a pirate for a little bit here. I've got to introduce a whole bunch of R's. So everything is radar, right? So radar means radio detection and ranging. And so we have that R that starts there. And then we get into real aperture radar. So this is the original radar. It's also known as a brute force system. So you'd start with a RAR. It was a military system to start with, so that's why it's a brute force system. I guess that explains everything to me. It makes sense, maybe not to you. So we have, it's like I said, it's the original radar. It actually has an equation that allows us to calculate the spatial resolution of microwaves, and that is detected based on the relationship of the wavelength and the antenna length. So here we can see the resolution is inversely proportional to the antenna length, which means that the longer the antenna length, the better the spatial resolution. So there comes a point that there is way too much antenna for the system. So for example, I think it was the Atlantis. I can't remember the name. It was one of the shuttles. It was part of the SRTM thing. I can't remember. The the boom on it, which was like the antenna length was 60 meters. This is crazy. That's crazy, crazy long. And still we were getting like, 5 kilometer resolution. Like it was terrible resolution. So they knew that this was going to be too difficult. They did use it on the ground. So you can see an example at my picture of one here of what RAR looks like. So we needed to find a way to reduce my spatial resolution, but yet not increase the antenna length. Let's just say spatial. So they came up with something called synthetic aperture radar as the computers improved. SAR is, it's not just satellite based, it's also airborne, but SAR now reversed that inverse, right? So it now says that the resolution is going to be related to the antenna length, like direct proportional. So we're looking at now the smaller the antenna length, the better the spatial resolution. So you do still need an antenna. Like you can't just like let it disappear. So there was no way to like make it infinitely small. So we still have a limitation with spatial resolution. But yet the antenna could be a virtual antenna. So the virtual antenna could be like super long, but the actual physical antenna could be super small. So the mathematics behind it just reversed what the RAR was. So everything we do now is actually SAR. You actually almost never see RAR. And in the biomedical industry, I don't have it, but they have attempted using SAR with the breast cancer detection and have had some success, but most of it's just like more of a radar-based system rather than SAR. Then we have side-looking airborne radar, which is SLAR, and this is what we have on airplanes. You will see people say SLAR is SAR, and that's what I was mentioning before. It can be airborne as well, just more commonly known as SLAR if it's on airborne. This one, both of them actually look to the side. So they're always side looking, they're never straight below, and the reason is just so that we can get some coverage on the ground with the footprints. So you can see a picture here, this is SAR, and this is a picture of SLAR. Then we have more. So if we take SAR and we start interpreting it in different ways. So the first one is polarimetric synthetic aperture radar, which is PULSAR. And we use pairs of letters to describe what the polarization is. So anything that says H means it has a horizontal polarization. Anything with V means it's got a vertical polarization. So the first letter of the that you put together, it means it's the transmitted orientation. The second letter means it's got a received orientation. So an HV means it sends out a horizontal wave and it receives a vertical wave. So a like pole system is when we have the same orientation. So we send out a horizontal and receive horizontal, or we send out vertical and receive vertical. Then we also have cross pole, which means that we send out horizontal, receive vertical, or we send out vertical and receive horizontal. There's also something called dual pole, which means that there's two polarizations. Like we can say, okay, I send out horizontal or receive horizontal, and then I send out vertical and I receive vertical. The other one could be quad pole. So if we have quad pole, now it's known as all four. So the system can do HH, VV, HV, and VH. And this is an example of a polarimetric synthetic aperture radar. It's actually used mostly for thematic mapping and identification of classes. So there's a lot of classification. There's also something called decomposition that we do, which will tell us more information about the materials and the properties of the materials on the ground. So just kind of an interesting thing. If you look carefully in the water, you can actually see waves from the different boats, which is also kind of an interesting thing too. Back when they made the announcement about the RadarSat constellation, Stephen Harper was the prime minister, and he was carrying on about how we're going to be able to track the enemy because of this. And of course, all the scientists were laughing and were like, yeah, you can track the waves, but how do you know it's an enemy? You can't see the person. You have no idea. So it was just like, yeah, I mean, there's a military side of things, but they also know that it does this. so they're very aware of that. All right. So some more SAR stuff, more R's, more pirate talk. We have interferometric synthetic aperture radar. This is DEM creation. So this one's kind of neat because we take two images and we put it together and we look at phase differencing, and then we can create a very accurate DEM. And in fact, the accuracy of an INSAR image it can be sub-centimeter in dry areas. So as soon as you add changes to the land or anything with moisture, it's not going to be very accurate. Then we can add to that one, and we can do differential interferometric synthetic aperture radar, and that's known as DINSAR. Now we use an INSAR image, and then we can use one more image from a different time, and we can put them together and detect change. Or we can take two INSARs and two INSARs and put them together and see if there's a change. Or we can do full stacks and see if there's a change. So I did triplets when I did DINSAR with the Arctic and looking at the changes of the Earth's surface based on permafrost melting over a season. And this can be accurate to millimeters, which is incredible because these satellites are 900 kilometers away. So the ability to detect change with this is absolutely incredible. That's why they could use it for monitoring land heaving for fracking. So this is almost more accurate than using a GPS system. The horizontal is not as good because we're dealing with a longer wavelength, but the vertical is really, really impressive. The horizontal is about 15 meters by 10 meters, but if you're looking at a large land change, then it definitely makes sense. Like a whole volcano, definitely, DINSAR is the way to go. The last but not least, we have polarimetric interferometric synthetic aperture radar, which is also known as POLINSAR. And so this is used in forestry. It's used to look at tree tops, measure tree heights, because we can see the bottom and we can see the top of trees with SAR because we can see through it. We also can get volumetric studies within it, so we can measure the actual features of the forest. So this allows us to create a classification of the type of tree, but it also allows us to create a 3D physical model of it at the same time. So again, in forestry, very, very powerful. I'm sure there's other applications, but I haven't seen many of them as of yet. So here is some examples of what you might see. So we have INSAR, which is showing us um, the the height in this case, height change, I guess. Um, I'm not sure what LOS stands for, but you can see that it shows actually phase changes. So every color change is like a new wave. So I go from dark blue to dark blue, and I've had gone through an entire like phase of my wavelength. And then over here I've got my DINSAR, so we're looking at where has it subsided, and it's showing the accuracy here. It goes from 0 to 3 centimeters. So you can see up to less than 3 centimeters from red to pink, or if you go from blue to blue, that's 3 centimeters over 5 kilometers, and it'll tell you that physical change. So again, very powerful for measuring the height changes of the Earth's surface in large areas. Then we have the POLINSAR here, which is classifying, and we'll also have heights. So it's telling us the heights of the different forest parts. So you can see everything from 0, so there's no trees here, all the way up to like high, which is going up to 15 meters in height in those trees. So again, very, very powerful tools with this. Things that you can't do with optical light. So you can't take two satellite images and do stereo imaging. It just doesn't work very well. You can do it with photogrammetry, but not so much with satellite. With microwaves, you can get heights, and that's also really exciting to talk about with this. So I think I'll talk about this one, and then I will. Actually, no, I'll talk about this one. I'm going to go with this one. And then I'll shut this one down, and we'll start another video so you guys aren't listening to them too long. So here's the polarimetry methods. So polarimetry is a lot of math, as you can imagine. A lot of software is already built to do all of this for you, so we're good. So the first step we need to do in polarimetry is calculate the amplitude of a polarization. So we have the energy that we've received in the x and y direction. And we can calculate that using this formula. Then we can calculate the orientation of the polarization. So what direction is that polarization? And then we can calculate the ellipticity angle, which also tells us like what direction is that ellipse that it's creating, because it's kind of like a blob. It looks kind of like a teardrop as it comes down to the Earth's surface with that energy. So with polarimetry, we have this fancy sphere, and this is how we represent our data for polarimetry, and that's the Poincaré Sphere, and we are trying to calculate phi and chi. That's supposed to be a chi, and they are kind of like latitude and longitude, and those are what we use to identify our polarizations. So here you see H is along here, so that would be our chi, and the vertical is the psi. And then we've got all different angles and orientations and the math, and then we have what we call Stokes Vector that's also in the center here, which actually helps us define it. So I'm going to move on to Stokes Vector. Don't get super hung up on this. Just imagine that with this sphere, I have my orientation, my polar orientations that are kind of like looking at astronomic coordinates. So think of it in terms of astronomic coordinates and that is based on the direction of the blob of energy that I send down from microwaves. Then we have Stokes Vector. Please don't memorize this. This is all based on what it's all about, really. Microwaves use a Stokes Vector, as an important tool to calculate how much energy we can find in the wave, and then how we can identify different features within it. And this is how we can we use these values to help decompose our future factors that impact the wave later. So we have the wave vector, which is like in our two orientations, which is E, and then we have EX and EY, so one's horizontal, one's vertical. And then we can break down those pieces into these components. So we have I, O, Q, U, and V, and I've broken them up in here for you to see. And so the I/O is the total amount of energy in the wave, and that's the first parameter that we're worried about. How much energy is there? The second one we're worried about is how much the polarization tends to be vertical versus horizontal. So if Q is greater than 0, it's going to be vertical. If it's less than 0, then it's horizontal. And then we also look at the tendency of the polarization to be oriented at 45 degrees. So if it's positive 45, it's greater than 0. If it's negative 45, it's less than 0. And then delta is the phase difference between the vertical and horizontal components. So that's where we would calculate that. So you can see that it's got the other option of the 2 times E, Y, EX cos delta. And then the last of the Stokes vector parameters is the handedness of the polarization. So is it right-handed or left-handed? And it will tell me if it's greater than 0, it is left-handed. If it's less than 0, then it's right-handed. So good old coordinate systems that we're looking at. So going back here, that explains like these values here, the Stokes vectors. So is it left-handed or right-handed? That's number 4. Then we have S1, S2, and S3 for Stokes vector. Last but not least, in the mathematics side of things, the heavy mathematics of polarimetry is the scattering matrix. So once we have S is an element of that's a complex number that describes the phase and amplitude of the transmitted and received signals. And then we kind of combine them into the vertical and horizontal, and then the cross poles as well. So this matrix, again, I'm not making you guys do the math on this because they're big. It's a programming thing that you would have to do. It's really hard to take just a small amount and throw it in there. What's nice about this using the scattering matrix is that it describes the relationships between the incident and scattered wave fields. So you'll actually see this in transmission as well in electrical engineering. And so this would look very familiar to anyone who's familiar with S11, S22, S12, and S21. And then so we can say, okay, in this corner, the idea here is that, okay, how much of this energy was transmitted and then received? So that's what that is in the vertical sense. And then here, if I send it vertical, and how much was received horizontal? And it really like creates that mathematical relationship for me so that when I look at it, I'm like, oh, you know what? I'm going to analyze SVV and SHV because there is a huge contrast between the two, and I want to see why that is happening. So using all this crazy math, we would take the information that we have and we would start decomposing it into different kinds of classification methods. And so if you were to download Sentinel Toolbox onto your computer and then run an image in there, you would actually find that it shows up as you'll see the breakdown of like intensity, and then you'll see phase and amplitude, and those are broken down for you, and then we can actually see the vertical and the horizontal, and you can do it all for free with that, and you don't have to do any math. You just have to know the process of doing so. So that's a brief introduction, the 29-minute introduction here of microwave remote sensing. I'm going to get into Objective 9.4 in the next video.